No idea why would they do that.
All right, thank you, Matt. Next, we're going to move on to the group report with Ben Sims.
Oh, are you on a group report? You said group report on the very first line. You got all confused. Your very first line of your talk was group report.
Say group report?
Yeah, what I think you say, good. Let's check.
I don't know.
Is it group report?
Yeah.
Yeah, got me confused about that. We haven't done the experiment, he's reporting on it. You did it last night or what? This morning?
Last night.
Last night, yeah.
Okay, so my name is Ben Sims, and I'm going to be reporting on experiment 2, the bomb calorimeter experiment. And our group was Austin, Peter, Mason, and I. And so we're just going to jump right into it with a brief introduction. And so basically, the point of this experiment is to prove that the heat of combustion can be determined from an oxygen bomb calorimeter. It can be defined as the number of heat units liberated by a unit mass of substance when combined with oxygen in a constant volume enclosure. And so if we take this experiment and we look at the calorimeter minus the fuel as our thermodynamic system, we can then use the first law of thermodynamics, and I'll explain that a little. We can start with the first law. We can say that we're not doing any work here, so work is 0, and then it comes out to be delta U equals Q. And so what is delta U? Delta U is, can y'all see this, by the way? Everybody? Okay. And we know in this case we have no kinetic or potential energy, so these terms both go to 0, which just leaves us with delta U equals delta little u. And in this case, we, in these conditions we were given, we can say it's an ideal gas, and delta U for an ideal gas comes out to be mCv delta T. So this right here is where we get our very ending equation, Q equals mCv delta T. And with just a little bit of rearranging, you can see that mCv is Q divided by delta T. And the apparatus and equipment we'll be using to conduct this experiment is right here. I mean, you see we have bomb lid, bomb housing, the lid locking ring, basically everything you see here. And let's go into it a little further. This is the setup we had in the lab. And 1 was our oxygen tank we used, 2 was our stainless steel bomb, our digital scale, and then our bomb containment tank. And here is the nutrition facts from our unknown fuel. And you can see that these calories is 200, but that's misleading. It's actually 200 kilocalories. So the value we should get for calories per gram is going to be 200,000 divided by 57 grams for the serving size. And that should give us about 3508 calories per gram. And this is the value we'll use when trying to determine our heating value. So we ran 3 separate scans for about 10 minutes each, and these were the results we got in temperature with our initial and final temperatures displayed. Here's test 1, here's test 2, and here's test 3. And so now, what do we do with these results? Here's our analysis. Like I said, we start with finding our mCv of the calorimeter using the value from our nutrition facts. And we found to have about right at 1,700 calories per Kelvin. And then we'll go, yeah, so now we go on to find the heat of combustion, which is Q for each test. And we had to Here, I forgot to say it in the previous slide, but it's shown here as well. We had to make adjustments for our, the amount of wire that was left over because it added an extra 23 calories to the system. So after each experiment, we had to adjust for that. And you can see this adjustment is made in each one here. And if I go back to the previous slide, you can see it's made at the very top where we added 14. So now let's go on to talking about our thermal capacitance, which is kind of what we were looking for in this experiment. And you see just the simple calculations for each one. And that is also with the adjusted wire value. And then we'll go on to finding our mean and standard deviation of each number. So our mean value was around right at 3,700 calories per gram, which is a little high for what we were expecting, but standard deviation is also high, so our number's kind of a little incorrect. And so in conclusion, what does this data tell us? So here is our final number. We were saying that we're getting about 3,700, give or take 100 calories per gram, which is higher than the value Sour Jacks displays on their bag. So what does this mean? Is their number incorrect? Is my number incorrect? Well, let's talk about a few sources of error. And so these numbers are comparable, so we're in the ballpark, and that's a good thing. But there's probably some error in the system, so what could some of these errors be? Let's see. So we didn't really have a known fuel sample. In previous week's experiments, they got to test benzoic acid and use that known fuel sample to help with their Q values to find adjusted MCV values that you could say remain constant to our test. To the unknown fuel sample test. But for us, we didn't have that, so we had to jump straight into with the gummies. And so our MCV value probably wasn't constant, even though we're supposed to assume it is. So that could be a potential source of error. Another source of error is we did not account for enough wire being left over. We said the value was 11 when it actually could have been 13, 14, 15. Maybe there was some left over that we didn't see. Or maybe our samples were stale, past their shelf life, but that's about it. And so here's my references, and are there any questions?
I actually have a question. On your data analysis heating value slide, that one.
Yeah,
In test 3, why did you subtract the entirety of the wire?
because we had no wire left over.
So that would mean that none of it was burnt up.
We'll say that one more time.
So you have 23 minus 23.
Right.
That's taking out all the calories of the wire. So you're saying none of the wire was actually burnt up at all.
No, all of the wire was burnt up.
So the second 23 should actually be 0. Because in that equation, you're taking out all the calories from the wire, saying that there was no added calories in there from the wire. That would mean none of it burnt up.
No, it means all of it burnt up.
You have 1693.27 times 25.83 minus 23.76.
Right.
Minus 0.
Right.
So when you do that minus 23, that's the 23 calories from the wire being burnt up. So you're taking that out of the calories that you're calculating.
Yes.
And what you did, you're doing minus 0. So you're saying that the wire didn't burn up at all and added no heating value to the water.
Correct.
So you still had the entire wire left over afterwards.
No, we had no wire left over. Maybe I made an incorrect calculation.
I think it should be 23 minus 0.
23 minus 0.
Yeah, so you just have minus 23 calories.
Okay.
Subtract what is burned.
Okay. So there was a mistake on my part right there.
Because all those numbers, what you should be subtracting is just, you should be adding 14. The last is not. So 9, 11, and 0, right? That's your leftover.
Right, right here.
Yeah. So you have to subtract 23, subtract 12, and subtract 14.
Correct.
As opposed to you subtracting 9, and 11, and 0.
Okay.
And the other got really worse than the last one. But if you go back to your very first slide, you start off with a problem. Second one. Yes. What is the first law of thermodynamics? Maybe it's probably my fault. I gotta be careful. When is that true?
This is true for a closed system.
Right? And what else?
The control of volume. Control mass.
All mass and what else? What are the assumptions going to that? Q minus W is not delta U. Q minus W is actually delta
I mean delta E.
delta E. So there you go. The full form is delta E. Now delta E is equal to delta U plus half E squared plus GZ, right?
Mhm.
You can't have delta U is equal to delta U.
Well, it's supposed to be, I don't know if you can say, it's supposed to be a capital to a lowercase.
No.
So it's
What is it with capital to lower? Difference from capital to lower is what?
Specific.
Specific. You're multiplying by mass, not multiplying by mass. It's got nothing to do with U's and E's. You start off with an E, right? And then E is equal to U plus kinetic plus potential. And then you say MCV delta T, that's a bigger problem. Why is it MCV delta T again?
It's for an ideal gas.
Ideal gas.
Internal energy ideal gas.
What is your substance?
Oxygen.
That's what you're burning?
Thought we put oxygen in
What is the substance that you're trying to find the calories from?
the gummy bear.
Gummy bear. That's not a gas.
It's a solid.
It's a solid. So what happened now?
And then you can't assume it's an ideal gas.
It's got nothing to do with ideal gas. The gas is not, first of all, ideal gas delta U is not MCV delta T. It's got nothing to do with gas or solid. Delta U is always MCV delta T. Delta H is always MCP delta T. It doesn't matter, solid, gas, liquid, makes no difference. Right? But then, there's another assumption, right? For a solid, CV is equal to CP. Or for a liquid. Why is that again? We talked about this. Maybe in the other section.
See?
Solids and liquids are incompressible and they have very high densities. Taken together, CV is equal to CP.
Okay. It has nothing to do with the R value.
Nothing to do with R values, nothing to do with the gas track. Okay, next. You had 7 minutes, by the way. Your class is really talking too long. You're all going to fail at this point. Because you're losing points for no reason.